is year 2 of the Polar Cap Patch Grand Challenge. We have several presenters in this session and then several in the one after the break. Through fortune or misfortune, I think we ended up having slightly fewer presenters than we thought we were. So everyone who I told you had 15 minutes, I think you actually have more like 20 minutes. But I figure that means more time for Q&A, or if you want to take a little extra time to go into your slides, great. But to start, I'm going to give a short introduction. This was originally supposed to be Lindsay Goodwin, but she unfortunately had to leave the meeting earlier this week. So I will be reusing some slides from the Grand Challenge last year just to give some background, although I think most people here know, so we'll flip through those quickly, but then go through some more things that we'd like to focus on specifically this year. Thank you all for being here, and yeah, we're hoping to get some good discussion. Let's see, does this? Okay. Okay, so this is our formal Grand Challenge title. This is what we all call this session. Again, this is kind of just some background from last year. They are large-scale density enhancements, typically thought to be twice the background in the F region. There are various publications that have shown them for various, this is a TC one of a, oops, I don't even know what's going to happen here. If I do that, does anything happen? Basically, they move across, they tend to merge from dacite plasma, get pulled through the center of the polar cap, so from sunward to anti-sunward, which I'm going to be clear about, because when we go into some other things, people often talk about if something's moving poleward or equatorward, and in the polar cap, it's technically both. It's poleward and then it's equatorward because you're moving from the sun side, the day side to the night side. And then they either recombine into the auroral oval in the night side or get pulled into the day side into one of the lobes of the convection pattern. Honestly, to my understanding, that's not entirely clear or well-defined. So these have been known in the literature and our collective mind state for quite a while, and have been used for quite a while as a indicative of they're these blobs, they're in the polar cap, they're something you kind of have to know and deal with. There's several different generation mechanisms that were proposed, but they're predominantly thought to be a winter time phenomena, although even that I think has changed recently. These classic patches are what I just described. You have dense dacite plasma pulled into the polar cap and it somehow segments. Even that, as we've seen from some presentations last year, may not be true anymore. There's a concept of hot patches, which are patches that are formed instead by soft precipitation and therefore have a higher temperature than their surrounding plasma rather than a lower temperature. There's a tongue of ionization, which is a continuous stream of plasma that is brought from the day side to the night, brought into the polar cap. And I think Roger showed some results last year that really raises the question of, well, are patches actually a distinct thing from a tongue of ionization, or are they just a very specific view of a tongue of ionization? And do any kind of slicing mechanisms, are they practical? Sun-aligned arcs are another density structure you see in the polar cap. Some kind of aurora that I believe happens on some unusual magnetic field topology where it's twisted so that you actually have something in the middle of the polar cap where you supposedly have open field lines. Poleward moving auroral forms, yet another candidate in the literature for something that could be patch-like that shows up in the same field of view. Traveling ionospheric disturbances. Sheng Rong has done a lot of work on this, and I believe we'll be presenting at some point, I forget whether this session or next session, on, well, if you look at things that typically we would consider traveling ionospheric disturbances, and you look at them, and you look in the high latitude region, we see very similar things. So are some of these things actually TIDs? And then finally, this is kind of a new thing, and one of the things we really wanted to explore, especially this year in this session, atmospheric gravity waves. And this came out of several discussions I've had with colleagues who are much more knowledgeable about atmospheric waves than me, seeing things in data in the polar cap that they say are waves, and I see them and I think they're patches, and we could never figure out a good division, like how do you tell one from the other? How do you know? And aside from the fact that we just traditionally have not talked about waves very much in the polar cap. So part of the things we hope to get out of the session is to start bringing in this discussion of, well, okay, let's just not talk about them. Let's see if we can figure out if this is a thing, if this is not a thing, if this is a thing that exists but is small and we don't have to worry about it, all of those good things. So yes, one of the things that we're potentially going to do as part of this grand challenge is come up with an updated definition for patches. This is more going to be the focus for next year, but just to kind of remind people that is something that we might have a responsibility to the community to think about, just a result of this grand challenge. And I want to be clear that the entire point of this 3-year grand challenge is not just to come up with a more specific definition for a patch, but to really look more holistically at, okay, what are all of the things, what are all these blobs of density that occur in the polar cap? What are all the mechanisms that might cause them? And can we make sure when we're talking about large mesoscale structures in the polar caps, we are considering all of the mechanisms that may be important, rather than assuming everything falls under one bucket, and therefore making incorrect conclusions about cause and effect and drivers and whatnot. Again, I think I talked about this last year, but I do think this is significance beyond just semantics and definitions. And the overall pattern of our grand challenge. So we are in year 2, and this year we're focusing on, again, these TID generations and thermospheric perspective, as well as small-scale irregularities within patches. So yes, this year's themes. So this is the new stuff. So thermospheric contributions. There's kind of, from my view, some very open questions, such as how much does the neutral atmosphere contribute to patch scale structuring? And some research has been done on this topic, but not very much, certainly not as much as patch dynamics from the magnetospheric perspective. And my personal kind of opinion of why that is that observing neutrals is typically much harder than observing ions, and making observations of the polar cap of anything is typically much harder than doing anything at mid-latitudes. So observing neutrals in the polar cap is extra hard, and therefore we extra don't do it a lot, even though we definitely should. And then, of course, that falls into, because we don't have observations, it's hard to validate models, et cetera, et cetera. However, there have been some recent advances in multi-directional couplings for MIT models. So not just thermosphere driving things in the ionosphere and vice versa, but actually having two-way coupling, which I think might actually allow us to advance this. And we have some talks later that will talk about what's happening in that, why it's hard, and what we can maybe hope to see in the future from that. And then small-scale irregularities. These are small-scale plasma structuring, which is a traditional topic we often talk about in the polar cap. So plasma instability mechanisms, how patches seed smaller scale structures, how smaller scale structures impact patches, and in general, what's the relationship across scales. So we have these mesoscale things that have nice gradients in an area with nice fast flows. Yes, that's going to cause other things that we probably want to think about. So this is kind of just my illustration. This is a magnetospheric dynamics in polar cap. You have the auroral oval in nice green, which hopefully you can see on the screens. The cusp is in yellow, and with this very kind of traditional thought, which we already know is flawed, of patches moving from the sun side to the day side to the night side, anti-sunward, in some kind of progression. So now the question is, what if we add some kind of wave dynamics? And I'm not a wave person, so this is all highly speculative, but I wanted to kind of put forward some thoughts, just what I've had with other people, of different things that might be of concern. So I don't know if can anyone see a pointer? No? Okay. Can we see that? Okay, great. So, one idea, okay, there are waves in the polar cap because there are waves everywhere else on Earth. Why not? How does this influence the interior structuring of patches? And how does that potentially feed into instability physics and other such things? Another thought is a lot of times we talk about geomagnetic activity launching waves equatorwards from the auroral zone. But if you're talking about some kind of impulse, again, this is my very naive impression, so people who know waves, please correct me. Why would we not have something launched polewards as well? And is that something that needs to be thought about? Another thing, I know there are some ideas in the literature that, at least from the TADs, those can actually travel over the pole, and that has been proved in certain models from the Sharon Bodas and Erich Becker group. I'm not sure if either of them are actually here at this meeting. But if you have those kinds of dynamics, and you do actually have that bring, especially when those dynamics may cause equivalent or analogous TIDs, if you have a wave that encounters the auroral zone, what happens to it? That's a large, you have two energy sources and they are colliding with each other. So something is modifying something, and is that something we need to worry about? And then finally, because you have kind of this confined, it's not confined, the auroral zone is certainly a permeable boundary, but if you have things that are coming in from multiple directions in the auroral zone, like here, you're going to have waves interfering with each other. And is that a factor that might be, I'm sure it exists other places in the world, but is particularly apparent here where we have a small-ish region to look at. So just in text, a summary of everything I just said. Some of the other things, how would we tell the difference between waves, especially when we're looking at everything with different observational modalities, all of which have downsides and blind spots. And yes, again, if we're having these waves, when they encounter all these dynamics that we know are magnetospherically driven, what happens? So again, just finally, this is a prime example of the kind of figure that, depending on your background, you think is polar cap patches or gravity waves, or not gravity waves, TADs. And just over, this is our session one. Roger's going to be the next, and then Osti. Kunyu Zhu is going to do TID impacts on patches, Cassia Besser and Shengrong to follow this up. And then we have several more in session two, which I believe is going to be in a different room after the break. So thank you. If they have any questions to start, otherwise, I think Roger, come on up. Green button advances your slides.
Green button, okay.
Or just that.
Yeah, safer on the laptop. All right, can you all hear me? I apologize if my voice is a little weaker than normal. So I was asked to come talk about the efforts to model polar cap patches within the Center for Geospace Storms team. And I'm really gonna focus on some recent work modeling ion neutral coupling processes in the polar cap and their contributions to the creation of polar cap patches, or the evolution of polar cap patches. So by this point in the week, I'm sure that a lot of you have heard about the Center for Geospace Storms already. We are a NASA Drive Science Center. We're in the 4th year of this Science Center already. A major part of this Science Center is creating the MAGE model, which is a coupled geospace model covering the ground all the way into the solar wind. It is a complicated modeling framework on the scale of like a Earth system model, like a giant climate model, in that it is coupling together many different models of many different regions with different physics together. We have multiple science goals within the CGS team, but our CGS Science Team 2 is the one that is most directly relevant to this grand challenge. So Science Team 2 is storm time mesoscale ionospheric structure and global geospace mass circulation. So that science theme includes the formation of polar cap patches and tongues of ionization, and the feedback of ionospheric structure to the magnetosphere through ion outflows and mass recirculation. So within the MAGE framework, do I have a mouse? Yeah, I do. So my original ionosphere polar wind model, we have now completely rewritten and integrated into the MAGE framework. So we're now calling it HYDRA, the High Latitude Ionospheric Dynamics for Research Applications. And that acronym is a play on the name of Gamera, because I learned an awful lot about numerical methods and software techniques from Gamera and pulled them into HYDRA. But the point is that this model is one of our major tools for studying the high latitude ionosphere at very high resolution, and also covering not just the ionosphere, but also the polar wind above it, so that we can actually talk about the transition from upflow to outflow. So the full two-way integration of HYDRA into the rest of MAGE is still under development. We are hoping to release that by the end of this year. What I'm going to show you in today's talk has been one-way experiments that we've been doing while we're still working on debugging the two-way coupled model. But these one-way experiments are actually a really incisive tool for getting at how the physics actually works. So everything that I'm going to show you today was run as a two-step process, where what I do is I run the MAGE 1.25, which is the version of MAGE that is already open source and available to the community. It is a coupling between the Gamera MHD model, the Raiju ring current model, which is itself a rewrite of the RCM model, so it's a kinetic drift physics model, a potential solver for the high latitudes that we call Remix, and the TIE GCM 3.0, the latest version of the TIE GCM for the thermosphere. So I'm going to run a MAGE simulation, and then I'm going to take the potential from Remix, the electron precipitation from Remix, the neutral densities from TIE GCM, and the neutral winds from TIE GCM, and take them all as inputs into the HYDRA model. So the latest version of HYDRA, I'm using numerical methods very similar to Gamera. So we have 7th order spatial reconstruction. I'm doing some fancy trickery with my treatment of the pole, such that I do not have any numerical artifacts near the pole. That involved a lot of details with tracking potential on cell corners and electric field on cell faces and density on cell centers. If you're interested in numerical methods, I'm happy to talk to you more about how I got these simulations to produce these structures without any numerical artifacts near the pole singularity at all. So these simulations, they do a really good job at producing mesoscale structures in the polar cap, and it's a very low diffusion model because the numerics are so high order. So we can now ask, how does the drivers actually affect the structuring? And I'm going to do a bunch of tests where I drive the model with identical potential, but I change the neutral driving. And that's going to allow me to isolate the effect of just the neutral driving. So historically, the polar cap literature has really emphasized the electric field variability as the source of structuring in the polar cap. What I'm about to show you are a series of simulations where the electric fields are identical across the simulations, and yet the simulations are not identical because the neutral atmosphere is not identical. So I'm directly isolating the influence of just the neutral atmosphere portion. So the event that I picked for this is the same event from the Zhang 2013 paper that Leslie showed. It's a polar cap patch paper. It's a moderate geomagnetic storm from 2019. What's interesting about it is it's actually a very strong BY event. So up here, this component is BY, and it is strongly positive. And you're going to notice that in all my plots, that the convection pattern is skewed to one side according to that sign of BY. And that's a piece of why the results come out as complicated as they do. So the first pair of simulations that I'm going to show you, the one that I'm going to call GTR is exactly what's illustrated on this slide. So potential from Remix, precipitation from Remix, neutral density from TIE GCM, neutral winds from TIE GCM. And I'm going to compare that to a simulation that has the same potential and precipitation, but an EMSIS neutral atmosphere and zero neutral wind. So On the left is GTR, and the middle is the EMSIS simulation, and then there's a difference plot. And this is electron density at 300 kilometers. And it's not terribly interesting in the calm before the storm, but as the storm develops, you see we pull a tongue of ionization into the polar cap. And as the activity continues, you see that this tongue of ionization twists apart. It does actually segment and form something that kind of looks like a polar cap patch. And we get all these, mesoscale structures all throughout the polar cap. But we get different mesoscale structures in the two different simulations. So again, these simulations have identical electric fields. So all of the differences between these two simulations can only be coming from the neutral atmosphere. So that difference is not just a monotonic difference either. In this difference plot, some parts are red, some parts are blue, some parts are higher, some parts are lower. So somehow the neutral atmospheric forcing is changing the details of all the mesoscale structures that I get. And so now the obvious question is why? What about the thermosphere is actually leading to these differences? So I did another set of simulations where the left panel that's labeled with UN is the same GTR simulation, but then the middle panel that's labeled 0 UN is where I zeroed the neutral winds at a TI GCM. So it's still the TI GCM densities, but no neutral winds. And when you do that, if the neutral winds didn't matter, these simulations would be identical. But they're not identical. And that means that the neutral winds that are pushing stuff up and down field lines are actually playing a role in modulating the structures. So this is a simulation-based proof that it's not just about getting composition in O to N2 right, although that certainly matters for controlling your recombination rates. The neutral winds are also playing some kind of a role in the way that they are either pushing stuff up the field line and slowing their recombination, or pushing stuff down the field lines and accelerating their recombination. And again, this difference pattern is not a simple pattern. It's not like all red or all blue. The neutral winds have different effects at different parts of the simulation. So I have been trying to think through what is the best way to, in post-processing, go inside these simulations and figure out exactly what is going on, term by term in the equations. Obviously, everyone should recognize the continuity equation written in this form, where P minus L is chemical production minus loss. You can break up the divergence term into an advection term and a divergence of U term. That divergence of U term has a divergence of the perpendicular drift and a divergence of the parallel drift. The perpendicular drift in the high latitude ionosphere is just the E cross B drift. And in an electrostatic ionosphere, in a magnetic field that is itself a potential field, like the Earth's dipole field, there's actually a very simple result for the divergence of E cross B over B squared. It is this. It depends on the gradient of the natural log of B. This is basically a purely geometric effect that flux tubes need to obey in order to conserve magnetic flux. So if the magnetic field was uniform, the E cross B drift would be completely incompressible. In the high latitude ionosphere, the magnetic field is not exactly uniform. And so what happens if you imagine a loop of plasma, if you E cross B drift into a region of stronger magnetic field, that loop compresses in order for the magnetic flux inside the loop to be conserved. And so this expression is just the rate at which a loop has to breathe in and out in order to conserve magnetic flux. So if you substitute that in for your divergence, your perpendicular divergence is just that, and then parallel divergence can be written that way in an appropriate magnetic coordinate system. It turns out that if you divide the whole continuity equation by B squared and do a bunch of algebra, you can lump this term into an advective term and end up with this alternative form of the continuity equation that I actually find quite interesting. So this on the left is just the Lagrangian derivative of n over B squared. So if all these other terms on the right were 0, then density over b squared, or density over magnetic pressure, would be a conserved quantity as you move stuff around through the plasma. And the only way for that not to be conserved is if these other terms on the other side of the equation are not zero. So these terms physically represent chemical production, chemical loss, a parallel divergence, and then this last term is a purely geometric term that has to do with the rate of change of flux tube cross-sectional area as you push stuff up and down field lines. It turns out that fourth term is actually quite small. But what surprised me when I started doing this is that this third term is routinely not small. So I've gone inside the simulations and done like a term-by-term analysis. So I am pulling out the total production from EUV and Aurora and all chemical production processes, total loss from all chemical loss processes. These are production losses of O+ ions, by the way. But then here is that third term, N du parallel ds, along the field lines. And this is at 350 kilometers, so kind of near the F peak or just into the top tide. And that third term, these are all on the same color bar, is routinely about 100 per cubic centimeter per second, which is not a small number. It actually competes with the other terms. And that third term is also very highly structured. It has these patterns in it that are like red, blue, red, blue. I think what's actually going on there is that the simulation has generated traveling atmospheric disturbances, and so you actually have a variable neutral atmosphere that is modulating stuff up and down the field lines. So if you were to just look at production minus loss, it would look like that. But when you look at all four of these terms together, the pattern you get is actually different. Another way to think about this is when you take a flux tube from the mid-latitude ionosphere and pull it up into the polar cap, it is out of equilibrium. So it's going from sunlit into darkness, and it doesn't have enough time to re-equilibrate the distribution along the field line, and so it is trying to readjust itself. And as it's readjusting itself, the parallel motion is not going to be divergence-free as it does that. And so now I can go into these simulations and I can say, okay, if I compare the full tide GCM to a simulation with a zero neutral wind, how do these terms change? And that third term, the so-called leakage term, the N du parallel ds term, is quite different in the simulation with zero neutral winds than it is in the simulation with the full neutral winds included. So the neutral winds and their projection onto the field line that pushes stuff up and down is changing the way the field line, the way the parallel motions work as the flux tube is thrashing around. And the net production loss is quite different in the simulation with neutral winds included from the ones with neutral winds not included. So what does this all mean? It means that a specification of high latitude convection is necessary but not sufficient in order to predict the mesoscale structures that we're going to see in the polar cap. Simulations with identical high latitude potentials but different thermospheric inputs produce different polar cap structures. The perpendicular flows are quasi-incompressible, but the parallel motion along the field line is routinely compressible. So we cannot think of the ionospheric plasma as an incompressible flow in the parallel direction. And the field lines are routinely out of equilibrium and reconfiguring themselves. That N du parallel ds term is routinely significant, which is something I was not quite expecting going into this. All of this means that we need more measurements of thermospheric state variables in the polar cap. Honestly, I'm making the science case for missions like GDC with this kind of a statement. In this field, we have a lot of measurements of electrodynamic and plasma variables in the polar cap, and we have comparatively fewer neutral thermospheric state measurements. And so that's a major challenge for the community. So going forward, the CGS model team is very actively involved in rapid model development. We're going to have a workshop this August where we're going to talk more about this. The TiGCM hydra coupling that I'm showing you has been improved in a lot of ways. For those of you who are TiGCM users, we recently made a revision to TiGCM where you can ask it for a different secondary history variable we're calling WNC. A gory detail is the WN variable in TiGCM is actually the vertical motion relative to the moving pressure surfaces, which is actually not what you want if you're going to couple to a model like hydra and magnetic coordinates. So we figured out how to correct for the motion of the pressure surfaces and come up with true vertical motion in inertial coordinates. There is work in progress to couple WAC-MX to MAGE, and that will be coming online in the near future. The two-way integration of hydra into MAGE is also going to be coming online within, hopefully, by the end of this year. And we're also working on lots of post-processing tools to understand these simulations better. So those of you who saw my graduate student Michael Lundquist's poster this week, he has developed a Lagrangian tracing tool to go inside of TiGCM and follow a single parcel in 3D backwards in time and reconstruct the whole production and loss budget. And he also showed that it's not just chemical production and loss, the negative N divergence of U term is also significant in TiGCM when following a TOI through its evolution. And he is working on a version of this tool for Hydra as well, and we think this is going to be a really incisive tool for understanding the complete 3D Lagrangian history of production and loss over the life cycle of individual structures. So with that, I'll wrap up and take any questions. Edwake?
That was good to see the modelers capture a lot of structure at high latitude. But there are several definitions of mesoscale. So what is your definition of mesoscale at high latitude?
100 kilometers.
Oh, that's
because
too big for us.
Okay, so there is a reason for that scale. That's my grid resolution. So in these simulations that I'm showing you, it's the 1.25 degree TiGCM coupled to a 1 degree Hydra. So 100 kilometer scale is the grid of simulations at this. So when you get below 100 kilometers, we have versions of these that we can push to 50. But if you're talking about below 100 or below 50 kilometers, you're now talking about subgrid as far as these simulations are concerned. So that's the way I think about this is 1,000 to 3,000 kilometers is a planetary scale structure, like a tongue of ionization. And something that's 100 to 1,000 kilometers is a mesoscale structure that is resolved within the simulations we're doing. And anything below 100 kilometers is a subgrid structure that cannot be resolved in simulations like what I'm showing you. Toshi.
Thank you for the interesting talk, Roger. So at high latitude, unlike mid latitude, field lines are close to vertical, so the horizontal wind doesn't have too much impact on the up-down ion motion by the drag. So can you explain how the wind play a role for creating this field line velocity structure?
So the projection of the horizontal wind onto the field line is not exactly zero. It's only exactly zero right at the pole. So there is still some non-zero projection. The other thing is the simulations I'm showing you have a vertical wind in them.
Oh, okay.
And this is actually why we learned this the hard way, that the WN variable in TiGCM is the vertical wind in pressure coordinates. And we actually figured out what we're now calling WNC, which is the vertical wind in inertial coordinates, accounting for the motion of pressure surfaces. So yeah, there actually are vertical winds in these simulations. As you have impulsive Joule heating, you are launching traveling atmospheric disturbances. So the motion of the particles along the field line, it's a combination between the projection of the horizontal wind, the admittedly relatively small projection, because the angle is like 80 degrees, but there is also a vertical wind in these simulations.
Do you have any idea what creates that vertical wind in the polar cap?
So there's actually two different types of vertical wind. There's the vertical wind just associated with the moving of a pressure surface, right? So you heat the thermosphere and your pressure surfaces move up. That is a wind as far as a model in fixed coordinates is concerned. But then there's also a wind that is the motion across the pressure surfaces. Yeah, so there are both going on, but it's essentially the variable heating. You have precipitation, you have joule heating, you are pushing the whole thermosphere up and down. But you know, for an observational perspective, observations of vertical winds in the polar cap, there's not many of them. We don't have a lot of observational knowledge of that, and so that's, you know, something for the community to work on.
Okay.
All right,
Next.
thank you.
Thank you, Roger. Austin? Hopefully it'll download without too much. Go. Close this. Okay, good.
Hi, everyone. After that modeling results, I'm going to show what Roger is calling more of the electrodynamic data that exists in polar cap. We do need neutral winds and thermospheric information. RISE-RN doesn't provide that, not directly, but what I'm going to show is different types of the data that are available from RISE-RN, and largely what is being used in this community are the fundamental plasma parameters that come from RISE-RN. So RISE-RN operations, these are from 2009 to 2026. These are all the times that RISE-RN has been operating. For those of you who have seen similar plot for Pfizer, it doesn't look that impressive, yet there are data at very periodic interval from RISE-RN, and many of these data are actually in conjunction with other ground-based instruments, like the all-sky imagers, like I think there was an FBI operating for a while for more neutral measurements. There is an ionoson has been operating for many, many years before RISE-RN came along in the same location, which also looks at the same ionosphere that we are looking at. In recent years, in looking at the about 2024, we have been trying to run things a lot more regularly with a bit of a hiatus in 2025. So in 2024, this is what looks like this was the solar max year, and we tried to make the 10 to 15 day measurements runs for each month. So each month across variable geomagnetic conditions, we have runs, and you can see the day-night transitions here. What most of this run look like is this. We run 5-beam mode with E and F region observations. And this is what you see sort of typically summertime, the polar cap ionosphere. Now, polar cap ionosphere is quite dynamic. It is from all the various drivers or potential drivers that Leslie was talking about in the beginning of this session, we see the impact. And the impact is, even though we are looking at only with the 5 spaced beams, you still are able to discern the spatial structure of what you are observing. So many of these, look very traditionally like a patch movement. Some of it is background ionosphere. Some of this has perturbations on top of background ionosphere. For example, this is some data from August of 2024. This is a 5-minute integration data that you are looking at the background ionosphere with some actual structure. And the structure, if you just let's say, extract the maximum from that, you see some structure. This is not necessarily periodic, not necessarily a patch-like, but the variability exists, and that this variability is something that is something to understand more deeply than, well, yeah, it's variable. So similarly, when we look at in 2022, another summer-ish time, because in Resolute Bay, April is not really summer, but for our purposes, this is another long run where each day looks slightly different from the previous day. There are some intense patches, some not so intense, well, some intense density structures, some not so intense density structures, some look periodic, some don't. And so this was run with this 7-beam mode where you can see these are closerly spaced beams where you can see the difference in the structures a lot more clearly. So these are this 4 beams in the center. And again, some of these, if you are from mid-latitude background, you're looking at TIDs, you look at this L-shaped density structure and think this looks really like TIDs. Some of these have the classical definition of double the ionospheric, double the background density. Some of these don't. Some of these, so that variability, my central point is that the variability in polar cap needs to be understood better, because that will tie directly the observations to the drivers that we are trying to determine. And it looks like the neutral winds, understanding and observations will be critical for that as well. So in summary, we need to have a larger heterogeneous data, bringing them together to look at the polar cap density structures. But the riser-N data are available in conjunction with a lot of co-located ionosounds, imagers, and FPIs for a while, including some scintillation receivers. The data, obviously, most of you probably know, are available on CEDAR Madrigal database, SRI Miser database, and reach out to us if you would like to use them. Thank you.
Thanks for the presentation. I wonder if you have also an imager in Resolute Bay, no? Because that could resolve if you have a patch or you have something else.
An imager existed at Resolute Bay until 2022.
Yeah.
And then recently, the imager has been reestablished since beginning of this year, actually beginning of last fall. So
yes.
this is a RIGO imager from University of Calgary.
Yeah, because even sun aligned arcs can produce some
Yes.
density enhancements.
Correct.
And some of them could be sun aligned arcs here. And they could stay for a long time. So you see
Right.
something like a big patch,
Right.
no, an hour patch. Usually a patch is only 5 minutes, 10 minutes. No?
Mm-hmm.
So, and that's why it has that structure,
Mm-hmm.
very thin in your scale.
Right. Yeah, no, so the imager data definitely exists for majority of the time that the riser N has operated.
I have a follow-on question with that. My understanding is one of the challenges we've always had with imagers in riser is that it's possible, but it's hard to use optics-based measurement techniques when you have daylight for half the year. And I don't know if anyone has a very naive question from someone who mostly studies ions. Is there any alternative to that or additional ways we can, look to measure things that might be more capable or have capacity during the summer?
If you're looking for a spatially resolved image of the patch during the daytime, that's kind of hard. You could have a better riser N, but that can actually image the ionosphere. But if, David might be able to also tell you in the ionoson data, right? You see a lot more variability during when the patch moves. And ionoson, I don't know if the Caddy ionoson did this, but they produced a sky map of the sort, and that also gives you some spatial information about what is going on.
Just a simple question. I couldn't quite see the timescales, but on your, when you look in the polar cap and you see these patches like this, what's kind of the timescale? Do you normally see things that are separated by a few minutes, or do you often see 10, 20-minute patch-like things? What do you normally see, and what's the kind of timescale?
All of the above, I think. So that's where I was trying to show this, right? If you look at this particular data set, right, this goes for multiple hours, like the x-axis covers multiple hours here. So
Yeah.
this much section is 3 hours. Okay, so the one before, you have about 2 or 3 within 1 hour, within about 2 hours. Then you have something that is a slightly longer time scale structure that lasts for about 2 hours. Before that, you have, these are about half an hour structures. So multiple things that are seen, and often within these larger structures, if you look more closely, you will see a lot more finer structure going on.
Structuring like that. I mean, that kind of reminds me, when I see stuff like that, it kind of reminds me of what you see on the day side, with the flow channels coming out of the day side and all the forward moving PMAS type things. So it doesn't surprise me that is that pretty common to see that kind of structuring in a patch?
I'm not going to call it a patch.
Whatever you want to call it. I mean, I call it a patch, but.
Polar cap ionosphere. That's why I think my point is that the variability at polar cap ionosphere, right? It is, if patch is a dominant mechanism, or polar cap patch as we understand it, the classical way it moves, that's a dominant mechanism, but that doesn't negate other things because we see so much variability. It is not clear cut from the observational point of view.
Thanks.
Thank you, Osti. Then next we have Quing Yu. Okay. Presenter mode. Thank you.
Thank you, Ness. So, hello everyone. So this is Chun from UT Dallas. Today, I'm going to talk about the polar traveling atmospheric disturbances. And during the event, I presented on Tuesday, and their impact on the polar electron density structures. So, just to refresh your memory. So during the March 13, 2002 storm, there's an intense neutral mass density spike measured by GRACE and swarm satellite. And simulation results suggest that it is caused by a transporter TADs initiated from the downside and propagating to the dark side. So the period we are talking about is just highlighted by the, let me use the mouse. So it's just during this period when the IMBY has a strong negative component. And as you can see, the figure below, it shows the temporal variations of the neutral mass density. So as you can see, initially it's at the middle of these figures and then gradually propagate to the dark side. And the GRACE photon flying from the dark side to the downside, while swarm satellite flown from the downside to the dark side. So roughly, our simulations captures those intensified neutral density structure. That's what we presented on Tuesday. Then the question we asked is that do transporter TADs lead to transporter traveling ionospheric disturbances, TIDs? So Shenrong actually reported the transporter TIDs based on the GNSS observers during, I think it's September 2017 storm. While Toshi argued that the transporter TIDs may be associated with the TOIs or polar patches because the magnetic field lines in the polar cap are nearly vertical. So, as you can see on the figures here, the transporter TADs shown here is propagated from the down to the dark side, which is quite different from the traditional propagations of the TOIs or the polar cap patches. So it may just provide some insight to see whether this transporter TADs can introduce transporter TIDs. If so, then another question we ask is how do these transporter TAD affect the polar cap ionospheric density structures? So the simulation we made is just utilize the field line current to drive the global ionosphere thermosphere model. We couple the NCAR 3D electrodynamo model to facilitate this coupling. The aurora precipitation is specified by the imperial model that is a function of IMF and solar wind conditions called ASHLE, stands for the aurora spectrum and high latitude electric field variability. So here we just shows whether we captures the model captures, well, we know the model captures the thermospheric signatures while we can capture, whether we can capture the new electrodensity structures remains unknown. So on the top figures, the top panel still shows the density, the neutral mass density variations, while the bottom panel shows the electron density variations at 450 kilometers. Again, so it might be a little bit difficult to see, but you can see that as the transporter TADs propagates from the down to the dark side, there's also electrodensity structures formed on the dark side. And both the swarm and GRACE photon captures the electrodensity well, roughly. Well, this might be a little bit see from the back seats, but you can see when the observation shows some red-ish colors, it's co-located with what is shown in the model. So because the transporter TADs is propagating from the down to the dark side, so we can actually see their propagations along the 6 to 18 local time meridian. On the top shows the vertical wind, neutral wind, electrodensity, differential electrodensity, and the Mariana ion drift at 300 kilometers. While the bottom panel shows the same things, but it is at 450 kilometers. So the left part, so the arrow here shows, well, the propagation of the TADs. So, and it is the same in other figures. So as you can see, when you see a TAD propagating from the downside to the top side due to the joule heating, there's also a collocated disturbances in the electron density. While this electron density reduces due to the transporter TADs at 300 kilometers. And if we just do the typical standard techniques to derive the TIDs, we just do a moving window to extract the long-term variations. We can actually see some propagating structures in these signatures. So at 450 kilometers, again, we can see the TADs in the vertical wind. And there's simultaneously, we can also see some propagating structures in the electron density. But at this time, at 450 kilometers, the neutral wind, the TAD or TIDs tend to increase the electron density at 450 kilometers. Again, if we just do the detrending, we can also see some propagating structures, while it might be a little bit noisier than what we saw on the 300 kilometers. So what we found here is we are not only seeing the vertical wind, but also the vertical wind is pretty strong. It roughly exceeds 40 meters per second. Sometimes it can exceed 50 kilometers. And the electron densities are, so variations display a altitudinal dependent features. At 300 kilometers, the electron density decreases within the propagating structures, while at 450 kilometers, the electron density increases. Also, the background flow, ion flow, is actually in the opposite directions, of the propagating directions. So the propagating directions, the propagating occurs from the downside to the dark side, but the background ion flow is just from the dark side to the downside. So it might suggest this is not a, some propagating, some patchy structures that propagate from the downside to the dark side due to the background ion flow. It's probably likely this shows this is indeed a transporter TID. And also, although there might be a shift of the downside ion, the convection features shift on the downside, but this shift is slower than the propagating phase speed, as well as the shift stop on the dark side. So again, it also suggests this might not be the feature associated with the background ion flow, but it's highly likely it's a transporter TIDs. And again, so if so the perturbations due to the transporter TIDs can reach about 10% 10% of the background electron density at 450 kilometers. So this is the propagation of the TADs and potentially TIDs along the dark side. Let's take a overview for the electron density variations at 400 kilometers, 450 kilometers, and 350 kilometers, as well as the vertical wind and 450 kilometers. So although we saw that the transporter TADs can be very significant from our simulation, these transporter TADs may not be responsible for the formations of these very strong electron density structures on the dark side. Because as you can see on the second panel, these transporter TADs is actually lag behind these evident electrodensity structures, which means when the transporter TADs even didn't reach on the dark side, the electrodensity structures already forms on the dark side. So the transporter TADs may not be responsible for the formation of the very evident peak density shown in this plot. Then we actually did a term analysis of the ion continuity equation as shown by Roger earlier this session. So the ion continuity equations just meaning that the variations of the electron densities is a combination of chemistry, electric field transport, neutral wind transport, as well as the ambipolar diffusions. So if you can see those subplots where I put red arrows there, so you can see that the enhancement of these density variations is mostly likely caused by the chemistry. So, and this is on the this is actually some features in the aurora zone. So, which is associated with the soft electron precipitation in our that is introduced by our model Ashley. So, and these features, I don't think it's related to the transported TADs. It's just probably most likely just caused by the soft electron precipitations. All right, to sum up, so first we try to determine whether there are transported TIDs associated with transported TADs during this event. And we found that the transported TADs can need very strong vertical wind in the polar gap, which might lift the ionosphere. And the electron density perturbations associated with the transported TAD can reach about 10% at 450 kilometers. And both the Swarm C satellite and the GRACE follow-on satellite detect the electron density peak on the dark side. And GIDM well captures this electron density peak, but the electron density structures is not the TOI. And instead, this peak is mainly caused by the soft electron density, soft electron precipitations. And with that, I'll stop here and happy to take any questions. Thank you for your time.
Okay, so I have yet another very naive question from someone who doesn't spend a lot of time looking at waves. So some of the structures you're showing, when you are referring to TIDs and TADs, are we actually talking about multiple wavefronts or kind of single peak that you see in your plots?
Well, so in this simulation, we didn't just show the propagation of TADs as a function of something, yeah. But for this one, yes, this is a large-scale traveling atmospheric disturbances that propagating from the downside and can reach to the equator of the other side.
Okay, so you found TIDs and a TID, but they're not necessarily. The TID is not necessarily caused by the TAD.
The TID is potentially caused by the TADs, but the polar cap patch, the structures in the polar region, the electron density structures in the polar region is not necessarily caused by the TADs because the TIDs associated with the TADs is roughly 10% of the background electron density perturbations.
Oh. It's so it's not double, but it's not
Yes,
necessarily something that can be ignored.
Yes,
As
right,
Asti
right.
showed, the high degree of variability we see.
Yeah.
Any other questions or thoughts about that?
The clarification that you got about how much the TAD contributes to the polar cap density is real important results. So you mentioned that TOI is created by precipitation, but in your term analysis plot, you also have the strong transport term, the electric field term, that's also nearby, and that may be closer to the density peak. So is there a possibility that the strong convection, and you also have the reconfiguration of convection here, contributes to the TOI formation here?
Right. So for this part, so what the comparisons I did is try to see whether this spot hotspot is co-located with some certain parameters. So as shown in this figure, seems that the chemistry seems very exactly co-located with the overall electron density variations. The transport, well, the electron density, the E cross B transport terms seems has some displacement with the hotspot, and also the ambipolar diffusions might offset this E cross B effect.
Thank you. Bimmel, who's next? Okay. Thank you.
Hello, everyone. So in this presentation, I would like to give you some updates on our investigations of polar cap patches in SuperDARN data. So we are actually getting into operations. So polar cap patches are characterized by sharp spatial plasma density gradients, and existence of such gradients leads to reduced accuracy for over-the-horizon radars, transpolar communication, and navigation. So it is very important to detect such instances for the operational purposes. And polar cap patches are very common in high-latitude ionosphere and can be observed by a number of instruments. But usually, these instruments are measuring plasma density directly, which is not the case for SuperDARN. So the question is how well this plasma density variability translates into the signal that we observe in SuperDARN. So we've heard already a definition and how the polar cap patches are created. The operational definition typically used is that these are plasma density enhancements by a factor of 2 or more above the ambient that have entered or are about to enter the polar cap. But in practice, this patch definition tends to be a bit more relaxed. So what we were doing, we were trying to check based on our ground truth, so the patch detection using ISR, how well we can distinguish this patches related signal in SuperDARN. So here we can see an example of a automatic patch detection algorithm applied to riser data. So what it does, it is taking average plasma density between 200 and 600 kilometers altitude, and then from the resulting time series, we can detect these peaks that are fulfilling the operational definition of polar cap patches. So we use these detections in the data spanning 3 years. And based on these times of patch detections, we can extract the SuperDARN signal. And we use the collocated range beam cells. Actually, this is our average of 9 neighboring cells centered on the riser radar. Elevation angles have been calibrated, so we have information about elevation of the backscatter signal, and only ionospheric scatter from F layer was considered. So if we just plot echo detection rate for the specific detections, we can see that there is some increase in echo detection rate associated with polar cap patches in the afternoon MLT sector. So this was kind of showing some possibility of detecting some patches in SuperDARN, at least to some degree. So we've actually tested a number of approaches. I kind of divide them into like point-based approaches, event-based, and temporal. So basically, in a point-based approach, what we are doing, we are taking each measurement conducted with SuperDARN, and we are assigning it a label based on whether it belongs to patch detection window from riser. So we have this number of data points, and because it is a point-based classification, there is no relationship between the points. We treat these measurements as independent. And this was probably it was the first thing that we've tested with not much hope. And I will give some details later. But the second one was event-based, and this is probably a bit more physically sound approach, because we are now extracting the full windows of a patch event in SuperDARN, and we are calculating properties of the signal within this window, and we check how statistical parameters, statistical properties of the signal over the patch window, how they are consistent with the label from riser. And the last one is the temporal evolution. So if we assume that as a patch is propagating across our field of view, it introduces additional signal-to-noise ratio, we can track this kind of peaks in the time series. So this was the third approach that we've tested. So for the point-based approach, we've used 4 main SuperDARN parameters. So the power, elevation angle, line of sight velocity, spectral width, and with an addition of UT time. Based on the results, UT time was more important than any of the SuperDARN parameters. So it is not very good result for the operations. Basically, you can just make a model that predicts that you detect a polar cap patch at specific UT time. So then we switched to event-based. So over each window, we are calculating, for example, the mean value of the SNR or spectral width, and so on. And again, we were detecting how well the labels are overlapping based on our detection. And here was another issue. So the most important parameter governing the patch detection was not UT time, was the window duration, which is, again, not a very nice result, because basically we are telling that anytime our signal is of duration of less than 2 hours, we are detecting a patch. So, yes. So then, the temporal evolution of the signal. And here's an example of an observation. The methodology is that we are taking SNR time series we are detecting all the peaks that we can detect. We are filtering them based on the echo rate, so we don't want to have peaks that are associated with echo rate less than 0.8. And we are checking whether the peaks are within the riser identified patches. And the problem is, again, that it is not easy to distinguish this patch versus non-patch signal. There are some specific times when you have higher probability of assigning the proper label. But I mean, for operational purposes, it's again not very nice. And I was investigating a bit more in detail conditions under which we have some issues. And what we've noticed is that there are some peaks detected by SuperDarn that are not identified in riser dataset. So we can see here the figure to the right shows this specific day as seen by riser, and we see some structure in the F region in the late UT time, and at the same time there are no patches detected. So patches are seen as this light yellow background. So in the late UT time, we have this like peaks, pretty significant peaks in SuperDarn, but they don't correspond to the detection in riser. So the question is now basically how good is our definition, and how well also is our automatic patch detection algorithm working on the riser data. So the results, to summarize, the maximum accuracy of patch identification using ISR measurements as the ground truth, they are basically comparable to random guessing at this point. So if you see a patch identified in riser, you can flip your coin to see whether you will see something in SuperDarn. In the event-based classification, duration of a window was the most important parameter out of the included parameters, basically highlighting the transient nature of polar cap patches. Signal properties within a window were more important than single point properties, and echo rate within a window was the third most important parameter. The best separation between patch and non-patch events occurs near the MLT midnight and afternoon sectors. So to conclude, basically, none of the investigated approaches allowed to reliably classify SuperDarn signal as a patch, indicating that there is no well-defined overlap with patches identified in ISR based on the operational definition of the polar cap patch. Cases of false positives, so no patch detected by ISR, but the signal indicative of patch detected in SuperDarn could potentially indicate issues with ISR-based detection algorithm or non-uniqueness of polar cap patches related signal in SuperDarn. So thank you.
So thanks for that presentation. No one really knows for certain exactly where SuperDarn echoes are coming from because the rays experience deflections. Particularly when the polar cap is very structured, there are azimuthal deflections such that where you're actually scattering from is different from where the superdarn propagation model would nominally assign that range gate. So expecting a one-to-one correspondence between the ISR that you actually do know where it's coming from and a specific range gate of a specific superdarn is kind of not realistic to hope for. And I would broaden this out to, you know, when superdarn sees an echo, is it anywhere near to a, say, TEC map identified patch? Or is it within 20, 30 minutes of something, a structure going over riser end? Some kind of broadening of your criteria to account for the fact that there's so much propagation uncertainty in the way superdarn rays actually go. So that's the one thing I can think of. The other is the ability to achieve perpendicularity, right? You can have a polar cap patch, but if the superdarn ray can't get perpendicular to be in it, you're not going to get scatter. Mm-hmm. So I think most of this comes down to HF ray tracing uncertainty, really.
Yes, that's why this will be our now next step. Garrett is actually doing the ray tracing part, so we will investigate it in more details. Already the way we are extracting the signal, it kind of takes into account this like slight changes in the propagation path. So that's why we switched from a single cell into like average of the nearby cells. So this was to account for this specific, this thing you've mentioned. So yeah. So along the lines of what Roger was saying, I'd be interested in seeing whether with this method, do you get statistically similar variability in superdarn detected things and what Riser is observing? Is it because, you know, like Roger mentioned and you said, it doesn't, it can come from variable things. It doesn't necessarily come from patch, or we don't know whether it is coming from patch or not. But so like to broaden the point of view, I'm wondering if you can even look at the just variability seen in your polar cap data with this method over a long time period, or something that matches the variability seen by Riser. I'm not sure if I follow, because this is based on 3 years of data. So it is statistics of this, right? I'm not talking about individual events. I'm talking about on average. Yeah, this is exactly this. On average, you have like the maximum of accuracy that I've ever seen was like 60% chance of assigning the proper label to your superdarn measurement. So, yeah, it is very problematic, but I would say like it is not, we should not look at it so much as like, do we see a polar cap patch? It's like we are detecting with this automatic algorithm in Riser, we are detecting the plasma density variability, right? So anytime you have this like increase and decrease of plasma density in the if region, is it related, and how well it is related to the power evolution in superdarn and so on, at what specific times you have the best alignment and so on. So, yeah.
There's an online question?
The question in the chat is, how does the 2 times density background figure in the current PCP definition for each of the radars? If 2 is changed to another number, would you expect changes in agreement? This is from Jason Durr.
Sorry, can you repeat the beginning?
Yes. How does the 2 times density background figure in the current PCP definition for each of the radars?
For each other radars, like, should I, is it about like different superdarn radars, like how it would affect it, or?
I think you could interpret it that way.
Yeah, okay. Okay, let's
Yes.
let's stick.
We got
to
a
this
response.
one.
It is yes.
Yeah, so here we are basically using just one specific radar, and we are learning, actually the algorithm is learning the properties of signal based on this single radar. You can apply it to any other radar, and it will just learn another like properties, I mean, of the signal. So this is not the case. In the temporal evolution of the signal, I am basically giving a very low threshold for the peak detection. So yeah, increasing it or decreasing, it would affect some labels, but I think it would just stay the same. I mean, I'm a bit pessimistic at this point, but yeah, I don't think that would matter too much.
The number, would you expect changes in agreement?
Yeah, so I mean, in SuperDarn, basically what you would have, like, based on the equation, you would have probably like 4 times higher SNR, something like this. But I mean, there are so many geometrical effects and so on. Like, yeah, I would not pay that much attention to this exact number of 2. We have this peak detection based on another algorithm, also applied to riser, which was giving many smaller peaks, like very frequent, because this definition, I think, was not using the specific 2 factor. I haven't tested it on these detections yet. Yeah.
Okay, Sheng-Rong, let's move on so you have a good chunk of time, and also thank you for those answers. Yes, you? Yes.
Okay, great. That's good news. I can turn many times. Okay, great. Actually, I have six or seven slides. Probably I don't need that much time. But so in the last 2 years, at the patch session, I have been talking about transpolar TIDs, and those TIDs are propagating anti-soundward, not like the what Chinyu were talking about, which transport also transpolar, but from dusk side to downside or the other way. So that is a different propagation direction. And in our observation, the fluctuation in plasma density, TEC, was something like 30%, sometimes 40%. So it's definitely not the classical patch, which is 3 times above the background, 2 or 3 times above background. So those are something on top of the regular patches, I would say. But today I'm going to talk about a different thing, and this is much more about the neutral impact, neutral composition impact on the segmentation of the time-hour ionization, which cause the plasma patches. So that's a new mechanism, new physics. And so this is my topic, and this was mostly the observation during May 2024. So I use ground-based TEC to demonstrate all these kind of effects. So there are lots of structures. We have TEC, storm enhanced density, TOI, patches, and the polar density hole. So these things are somehow connected physically. Before I go into that part, I want to show just a general storm time impact during this event. So what you see on the left is the U.S. longitude sector observations of TEC as a function of latitude, vertical axis, and the universal time. So the top panel is the original TEC, and you can see the storm time significantly enhanced the density in the northern and the southern crusted regions. And then the mid panel shows the difference between the storm day and the average day, several days before that. You can see the immediate response during the BJ southward turning, particularly in the southern hemisphere, the enhancement is much more significant. And the following data was the depletion due to the O2 and 2 ratio impact. And I want to draw your attention to the patches a little bit after the onset. The first one is somewhere around 19 UT. And then this blue region, I believe this is associated with the O2 and 2 ratio impact that I will talk about later. And then the patch come back 1 or 2 hours later. So this happened in the northern hemisphere. So the bottom panel is the differential TEC, and that's the fluctuation component on top of the background neutral densities. And so everything all of a sudden showed onset of disturbances around the same time in either delta TEC or differential TEC. On the right is in the dayside hemisphere, and left is American longitudes where we are on the night side when the storm started. So the night side hemisphere is different, but the onset, this is mostly penetration electric field, is very similar in an opposite way. So you see the density depletion in this night side longitude sector, and here in this American sector, which was on the day side, and you see the immediate enhancement. They are potentially driven by the same kind of penetration electric fields, except the electric field is opposite, and generally the opposite in fact. So this is the background. And the next one is okay, let's see. The movie doesn't want to play. Okay, this one. Okay, this one. So, okay, so this one doesn't work, but anyway, so my main point is on the mid panel. So this is a polar view of the total electron content. And day side is on the top and night side on the bottom. What I want to draw your attention to is not only the patch moving anti-sunward into the other hemisphere, it's also the blue region, which is the so-called the polar hole, electron density hole. So the movie is going to play again. So the bottom panel here is a snapshot. Now the movie is playing back again. So not yet. So you notice the blue region, which is low density, is moving this way from the morning sector across the noon into the afternoon sector. So that's very important feature. I really want to show that again from here. So at this moment, you see the blue region on top, and then it's moving this way to the dusk sector and then downward. So normally you think this lower density region is associated with the O2 and 2 ratio being decreased because the enhanced neutral N2 will be play an important role as to cause the recombination in the plasma density. And what's interesting is that structure is actually moving when the patches from lower mid latitudes moving into the polar cap region. So there are two things going on simultaneously. And the study, the snapshot here shows some of the features here. So the blue region here, and it's next by the tunnel ionization, which moving anti-sunward. So these are so-called kilograms. And these just show the SED plume moving as a function of time westward. into, mostly westward at the subsolar rotation speed. This is within the polar cap. So the vertical axis is the longitude for the given latitude. So the latitude here, this one, is about 70 to 75 geographical latitudes. So this is just showing how things moving in this longitudinal circle. And this top part is the dusk sector, and this is the dawn sector. So that when you see structure, which is tongue organization, moving this way, which is the eastward, that's indicating the structure is anti-sunward because this is on the dusk sector. When the structure is moving eastward, it's actually anti-sunward. The low density region you can see here, which is what I call the plasma density hole, and further into the polar cap region, and this was 70 degrees, and this was 75 to 80 degrees in latitude. You can see this is basically next to the TOI, it's moving this way. So, so you see these snapshots before in the movie, but I just want to emphasize that how the lower density region is moving across from dayside through the noon time into night side, and then moving anti-sunward into the night side. So there was an observation, the GUVI O2 and 2 ratio observation during the same time, indicating the depletion of the enhanced O2 and the depleted O2 and 2 ratio. So the observation was during 21 and 19 UT when this corresponding to this time, 2 hours into the storm. So our suggestion is that this lower plasma density is an indication of the O2 and 2 ratio depletion. And that depletion zone is convecting, co-rotating. Basically, it's co-rotating. If you look at the movie again, the Earth is rotating. The blue structure, which is depleted ionization, is also rotating. It's co-rotating, but it's not perfectly co-rotating. It's sub-rotating with slower speed. But anyway, that lower O2 and 2 ratio is moving across. That enhance the N2 particularly will play an important role, a chemical effect to recombine with the O+. So that way you have reduced O+, and that can provide a physical mechanism to reduce the plasma density in the dayside tongue ionization region, so that you, since like you cut the TOI into patch. So that chemical is basically play an important role to recombine with plasma and cut the tongue ionization into patch. So that's the physics I've been talking about. So that's my main result here. I'm looking forward to your comments. Thank you.
Hi, Shenrong. Thank you for this very nice talk. So we have Rise-Around data during this storm time, and what we see the ionospheric hole on May 11th, actually.
Yeah, so just the beginning of the May 11th, right?
Well, yes, before noon.
So, okay, so you're talking, so the storm started somewhere around 18 UT, and the first patch we observed was around 19. That depletion in the polar cap region I was talking about is a little bit after that. And this is the next day. Yeah, this significant depletion is obviously, so I don't know what part of depletion we're talking about.
Yeah, so we are seeing the ionospheric density hole around 4 to 6 UT.
4 to 6.
And correspondingly, when we do the, so we use the a chemistry model and doing the fitting, you see, of course, your O plus depleting, and you also see NO plus fraction
So
increasing.
you are talking about this time, I guess, 6 UT.
That's right, yeah.
Yeah, yeah. So I'm talking about a little bit earlier, just 1 or 2 hours into the storm. So the blue region initially somewhere over here in the morning sector and then rotating along with the Earth, sub-rotation. And when the patch is coming over, it's cut the patch into, the TOI into patch. Wenbin had a movie. I don't know, do we have time to allow Wenbin to show dissemination of O2 and 2 ratio? Do you want to do that?
We have 15 minutes before the end of session, so, and I have this reserved for discussion. I think David had a question maybe specifically for you. And then we'll.
Test? Yeah. Yeah, so like in our 2024 paper, the depletion in the morning sector happens like within tens of minutes, relatively, like incredibly quickly. And we see that in the poker flat data, the F2 layer is gone within a few minutes. So there's very little delay in that depletion beginning in the morning sector. And as you say, it spreads across. We then see it in Svalbard just maybe an hour later or so. So it's entirely consistent with what we've seen in the infrared scatter radar data. Yeah.
Okay, that's good.
And then there was one online.
Question online is from Jason Durr. Do you think this mechanism is more generically responsible for PCPs detaching from the TOI? That is, not just during this event, but most instances of PCP detachment during enhanced geomagnetic activity?
Well, I think there are different theories about how the TOI become patch, and there are different theories, I can say that. The chemical part is relatively new. I have never heard about this, actually. Maybe other people who do simulation know about that. What's interesting with this event, as David said, the storm impact caused immediately plasma density depletion or O2 and 2 ratio depletion at the very beginning of the storm. So timing is very important. And when the patch is moving anti-sunward into polar cap region, the lower density region is moving at the same time. So everything happens around the same time that can produce significant impact. How generally this process is, I'm not sure. When you guys do your simulation, and depends. I mean, probably depends on the timing of the storm. I don't know. I don't have a good answer for that. We can definitely looking at other events though. Yeah. Do you want to show Wenbin or?
Yeah. So we have about 13 minutes left in this session. Do you want to just, how large is the? There's a follow-up. Okay, there's a follow-up. Let's do the follow-up question. You want to bring the movie again?
The follow-up is, I guess the question is whether chemistry is responsible for TOI to PCP detachment, frequently given Rogers' prior publication suggesting that several of the suggested methods for this detachment are not feasible given MHD constraints.
Say that again?
Yes, of course. I guess the question is whether chemistry is responsible for TOI to PCP detachment, frequently given Rogers' prior publication suggesting that several of the suggested methods for this detachment are not feasible given MHD constraints.
I don't know. Roger, do you have any comments?
Sorry, large room.
So there is an old theory of polar cap patch formation that involves cutting a TOI into pieces through enhanced recombination in narrow channels.
Yeah.
Now that older theory invoked flow channels that would produce localized heating and accelerate the O to N2 reaction rate, because it's a very temperature-dependent reaction rate. What Shunrong is showing here is just an upwelling of N2 during the storm that is happening on like planetary scales. So like in order for this O to N2 ratio effect to cut a TOI into segments, you would need localized O to N2 enhancements, not
You
like,
need to have time for the chemical effect to be effective.
yeah, I think it's kind of hard to have composition structures that would be that localized. I mean, maybe in the cusp, because there's the cusp neutral upwelling, but I think what you're showing is more of a planetary scale effect than it is a mesoscale structuring effect.
Yeah, it's, I agree, it takes time for the chemistry to be effective. Depends on how fast the rotating of the structure is. But it will have impact on the ionization in the patch region, whether you really cut, how much you cut takes time to be effective.
Words about what has been said. When you have these large flows, the large flows last for tens of minutes. So it doesn't happen just in 1 or 2 minutes. They have a temporal evolution, no? And that can be observed with the SuperDAR. And SuperDAR is very good to see the velocities when you have structures. In the daytime, most of the time, you have some kind of structure. It could be the cusp, it could be tongue of ionization, it could be many things, no? And then, of course, in that moment, it's difficult to see where is the patch. But the good thing that these flows also turn the plasma around. And then the patch becomes elongated in the dawn dust direction. And that's very easy to identify after that. So if you identify large flows with a SuperDAR, I mean, you have a way also to know about patches.
You need the exact convection pattern. I think Wenbin want to show you a simulation. Right?
See if you can just disconnect that and leave everything else. Sorry to the people online, I don't think you're going to see this, but.
I'm done. Thank you. Are you leaving? Start a mirror.
Extended display.
This one, right? You say it?
Yep, that's fine.
Okay, but someone asked me to. So this one, this is my AGU talk a couple of years ago, and use a major output, major simulation of the storm. I just saw one movie. This is the neutral wind, and this is southern hemisphere. This is northern hemisphere. Just play the movie, you can see how the O2 into a storm occurred, how the O2 into develop, depleted in high latitudes, and then expand globally with the wind enhancement. Just show you, this is a 1 kilometer vector, and this is the O2 into ratio here. So let me play the movie. So you can see the wind. This is a quiet time. Also, there's a fixed geographical system. So the convection pattern moving with time, with UT. So let's. Yeah, this storm occurs, and then the blue area is the depleted O2 into ratio region. You do have some structures, and also it's correlated with the Earth and with the local time, and it's, you can see drifting changes with the convection pattern, with the wind pattern moving around the world. That's what I always just want to show. And in the southern hemisphere, we do produce this kind of vortex structure, but unfortunately, we couldn't reproduce it in the northern hemisphere. So we don't write paper and report that because we only produce one hemisphere. But anyway, this is the O2 into variation.
you do see the large scale changes or global scale changes, as well as some small structures. But that's about it. That's what I want to say. Okay.
Okay, we have 7 minutes in this session. How's everyone feeling? Any thoughts and comments? Asti, did you have something to show? No? Okay.
Thank you. Well, I may be the older person here in this room right now, but I do remember in the old times, it was not difficult to recognize the patches. No, using CEDAR, using the imager, no, and we didn't have Resolute Bay. We could see where the patches were. Now you have Resolute Bay that is a phase array, and you can see in different directions. So even in the summertime, you can know how this structure that is coming, how it's aligned. No, if it's rounded, if it's elongated, so you should be able to. I mean, it should be easier.
What it sees.
Yeah, yeah. So I'll just, this is, I just wanted to show this, what Riser saw during the event that Shenrong was showing. This sort of starts from, here, this starts from beginning of the storm, May 10th, but at around 18 something UT. And then we see something that is, we don't know what it is, but followed by this hole in the density. Can you see the oh, I don't know. My mouse is not there. Oh, there. Okay, there. So that is the hole in the density. At some point in May 11th, it comes back. The ionosphere sort of comes back, and then our, well, density structures return. And again, no, there is no F2 layer. That you're right. There is no F2 layer. It's just F1 layer. Correct. But on the next day, May 12th, more things come back. But so in the beginning of the storm, again, there is nothing in the F2. This is F1. These red things are not electron density. But when we look at so that this plot here, that is the ions that we fit for. This is N2 plus. Oh my goodness, I cannot see both places. N plus, N2 plus, NO plus, O2 plus, and O plus. As you can see, O plus is depleted, but NO plus has increased above 300 kilometers. So, and these are all information from different beams and strong velocities at the beginning of the storm and at the, well, later on as well. Oh, yeah. It's not, it's something non-Maxwellian. It is not. It looks like density, but it is not. So please, nobody use that as density. Well, it's in every beam, not. But anyway, that's not the focus of this meeting. It's just the whatever the density structures are restarting May 12th, but we don't see any other density structures as in this storm between the beginning till the May 12th. So that's what I wanted to show.
Okay, so any final thoughts or comments about any of that? Anything that we just discussed? We do have okay, Larry. Are you going to be at the next session? Okay, come on. Real quick, and while Larry's coming up, I'll tell everyone the spiel. So the next session is, I believe, in room 102 after, is that correct? 101, thank you, 101 after the break. I really appreciate all the different examples of things that we can see in the polar cap that, and all the variants of what they are, as well as everyone sharing their data. Over the break, if you have anything you particularly want to share, I think we are going to have a good discussion period in the next one too. Please feel free to email it to me so the online people can see it as well. It's just the HDMI, Larry.
That one?
No,
Okay. Oh, well. Here
here you go. Here you go.
This is purely entertainment. I pulled that. So what I need to do is show it.
Allow. Allow there, and I think my computer's disconnected. No.
I just connected that one already.
Yes, and then I think
You go up?
do PowerPoint. Presentation view. Yep, there you go.
Yeah, okay, this is just for fun. We were looking at the two-dimensional super darn flows, on the day side, and you can see the flow channel, the way the flow structure is, so narrow, going all the way from the basically the cusp all the way over into the pole. So we just pulled out TEC data from wherever, and just could see that tongue of ionization just following right along from this, probably a little more equator, we're just right up the pole. Just the correlation between the two just sort of just entertained me. I don't know if that's important or not, but just thought it was cool to see it. That the flow channel is so nice and isolated and localized, and the TEC just follows right along, giving you the tongue of ionization, just as a random time, nothing significant in terms of storm or anything.
Well, thank you. As I said, I really appreciate everyone's participation and look forward to more discussion next session. Have a good break.